Here. Here is the guy.
Come on, Coleman. Sorry.
It's okay. Although it's recorded, but I didn't do that. Whoever is listening, it wasn't me. Okay. Yeah, let's start a new topic. I should have a clicker. Why don't I have a clicker? Huh? Abby, you have one. Not on you. Okay, fine. All right, so we're starting a new kind of chapter in proteins. So far, we did our map of intrinsic factors, extrinsic factors, except for modification later on, functional properties, and now we're going to switch to, we're talking about enzymes. You love that topic, I could tell. Okay, and now we're going to talk about sources, different sources of proteins, and we'll start with the traditional ones. So we're going to talk about milk proteins, mostly casein and whey. So casein in the market can be found as sodium caseinate, calcium caseinate, or micellar caseinate. We'll talk about the production and the functionality, but first we'll talk about the chemistry of the casein protein. And then same with whey protein, we'll talk about the chemistry of whey protein, and then the production of concentrate, isolates, and their functionality or use in different applications. Soy protein, we'll talk about soy protein under legumes and oilseeds. Soy protein is the most traditional plant protein that exists in flour, concentrate, isolate. But obviously we have pulses, pea protein. So we're going to be talking a little bit about pea protein under legumes and oilseed category. We will for sure cover cereal proteins. The chemistry, the uses, different cereal proteins. I might not get to egg protein and depends how far along we can go. I always have the lectures ready to go, but sometimes I run out of time. And then we won't talk about like potato or almond or algae or insect protein, but they are emerging, and we kind of introduced some of that at the beginning of the semester. Okay, so I did keep changing my slides. I posted the most recent one just about an hour ago. I don't know which ones you printed out. You might have printed out the older ones, Coleman.
No,
When did you just print them?
right before I came.
Perfect. So then you have the most recent one. Because every time I try to update a little bit, it wasn't a lot of updates though. Okay, so we're going to jump into milk proteins. So what's the percentage of milk not milk, protein in milk? 3.4%.
3 to 4%.
Yeah, okay. I thought they were very specific, 3.4. Yeah, it's about 3.5-ish, around that, plus or minus. So, well, of this little bit of protein, we can get the caseins and the whey. Of course, what's the percentage of moisture in milk or water? 87, 88%. It's mostly water, obviously, milk. So from the solid, we have obviously quite a bit of protein and fat and salts. But so the proteins out of the I have 3 to 4%. Oh man, you're just like peevishly laughing. That's what I think. Okay, so right there. All right. So 80% of this 3 to 4% protein is casein and 20% whey protein. We also have a bunch of enzymes. Food enzymes are proteins. So enzymes in milk, there's this old table, FYI, but there are a lot of different enzymes, oxidoreductases, transferases, hydrolases, lyases. We already talked about all of those. But the most common enzyme that cause problems is the proteinase spasm. So this causes problem in terms of stability of the protein during storage of milk because it hydrolyzes mainly beta casein and causes aging and clotting of milk over time. So this is a very common or problematic enzyme in milk in terms of being a proteinase. Lipases, there are lipases in there, quite a bit of other hydrolases, but one critical one we use for determining the pasteurization efficiency of milk is the alkaline phosphatase, which is very thermally stable. And after pasteurization, to determine the effectiveness of pasteurization, instead of measuring microbial growth, takes 2 days, they measure the activity of this enzyme to determine the efficiency of pasteurization. Okay, so there's a lot of enzymes in milk basically, but we're not going to talk about milk enzymes. We're going to talk about the proteins that are important for functional properties in food. So we're going to talk,
Sorry, alongside measuring the enzyme activity for pasteurization efficiency. So if pasteurization was efficient, then enzyme activity would be low.
yeah, so it is a very thermal, stable enzyme. So if this one is inactivated, that means all the pathogens are killed because it's more thermally stable than the pathogenic microbe. So pasteurization takes care, as you know, from the processing of pathogens. Sterilization kills all microbes. But the pathogenic bacteria, this enzyme is more stable than them. And if it gets inactivated after pasteurization, that means all of your pathogens are killed. That means that the pasteurization was effective. Okay. So we're going to talk about casein and whey proteins. So in casein, we're going to talk about alpha casein. There's alpha S1, alpha S2. We're going to differentiate those. Beta casein, kappa casein. So we have those 4 different caseins: alpha S1, alpha S2, beta, and kappa. So, and if you look at a gel, this gel is actually not a regular SDS phage gel. This is a urea phage gel. It separates protein based on charge to molecular weight ratio. So if we run casein on a regular SDS phage, we won't have separation because they're very close in molecular weight. So if we run them on a urea phage, then we can see the alpha caseins, the beta, the kappa, this sodium casein isolate. You can see the alpha and beta. There's usually an overlap between the kappa and beta casein. Now the whey protein, so there's this gel at the top here. This is a regular SDS phage gel. So the most abundant proteins in whey protein is beta-lactoglobulin, alpha-lactalbumin, with about 60 to 80% beta-lactoglobulin compared to alpha-lactalbumin. But we also see immunoglobulins up there. We have some lactoferrin, and then we have the serum, bovine serum albumin, and the glycomacropeptide. So this is whey protein separated by membrane that usually comes from after production of cheese. And the production of cheese, you have the rennet that cuts the kappa casein into and releases the glycomacropeptide, which is soluble, so it stays in the whey tract. We'll talk more about that. So we can see some of that here on the top. That is retained in membrane filtration. It remains with the whey protein. So these are the minor components that we talked about, serine albumin, lactic transferrin or lactoferrin for short, and immunoglobulins. So you will find those in the weight fraction, but the major components that drive the functionality of whey protein is beta-lactoglobulin and alpha-lactalbumin. All right, so looking at the diagram of milk proteins, so we have the minor proteins and enzymes, so they are just not the focus. And then we have the caseins and the whey protein. Under caseins, we have the alpha S, kappa casein, and beta casein. And then under alpha S, there's alpha S1, alpha S2. And then you will see this A, B, C, D, A, B, C, D. What do you think this A, B, C, D refers to? Yes, genetic diversity, genetic variants. So they're depending on the cow and the different species, well, different, what do you say, varieties of cows? Is this a, what do you say? I mean, it's a species, breeds. Not varieties, oh my God. Okay. We're different varieties, you and I and everybody else. Okay, no, so different breeds. So they have different genetic variants, a little bit differences in amino acid composition. Not a lot of variations, but some amino acid variations with the slight differences in molecular weight. Now, under beta casein, we see these gamma casein here, and then under the weight, we see the protease peptide. So what are these? Beta casein over time gets hydrolyzed with the plasmin. The plasmin enzyme that I said is problematic, which breaks down beta casein. So the gamma casein, we'll talk about them later. These are hydrophobic mostly, so they stay with the casein fraction. And then if we're separating casein and whey, the hydrophilic fraction of beta casein, which is the protease peptone, stays with the beta protein. So that's when we fractionate whey and casein, and if we have hydrolysates of caseins, beta casein, we'll see these divided between the casein fraction and the whey fraction. So let's talk about caseins. So alpha S1, alpha S2, and beta caseins are phosphorylated. They're serine, mostly they're serine amino acid that has an OH. That's why you learn amino acid structures. So the serine with the OH is phosphorylated post-translational molecule. So a lot of these serine residues on these caseins gets the phosphate group. So this allows them to bind to calcium. Okay, and the calcium phosphate that the phosphates form bridges with the calcium and another phosphate on a different serine residue, and then it forms the calcium phosphate bridges that stabilizes some of the casein molecules within the casein micelle. So this phosphorylation plays an important role in the stabilization of the casein micelle, and we'll talk about casein micelle a lot later on. But this is the main function of the phosphorylation of these three caseins. Now, beta casein is phosphorylated, but the least phosphorylated. So it doesn't have as many residues of serine that is phosphorylated, and a big percentage of beta casein is hydrophobic. So it's the most hydrophobic casein among those four. So the most hydrophobic is stabilized within the micelle mostly by hydrophobic interaction. That's why, if you remember, I asked this question before, when we put the milk in the fridge and temperature of 4 degrees, some of this beta casein leaves the micelle and goes into the wave fraction. And why is that? You remember? Something about, huh? Exactly. So hydrophobic interaction are weakened under refrigerated conditions. They are strengthened with heat and weakened at low temperature. So some of the beta casein seeps out of the casein micelle, and we find it in the whey portion in cold milk. So yeah, that's what I said about earlier. They are calcium sensitive. You can precipitate these casein if you increase the calcium concentration, because then you can form more calcium phosphate bridges across different micelles, and then we can precipitate with increasing calcium. That's why we add calcium to milk during cheese production to enhance the yield of the curd. So kappa casein, on the other hand, is not phosphorylated, it's glycosylated. That means the OH group, but not of serine this time, of threonine, and another amino acid that has an OH residue. So it is glycosylated, has a carbohydrate covalently linked to the OH group, again via post-translation modification. That makes a portion of the kappa casein very hydrophilic, and we'll see the micelle, and we'll see that kappa casein is usually mostly on the surface of the casein micelle, imparting a lot of negative charges on the surface of the casein micelle, causing that colloidal system of caseins to be stable in milk. So the kappa casein layer around the casein micelle is what stabilizes the micelles in milk and prevent them from separating, keep them soluble. So we also talked about the casein having a high percentage of protein. Most of these caseins have up to 17% protein. So that reduces the formation of beta sheet, alpha helices, because proline is a secondary structure breaker. So we have mostly random coil, open structure, which makes the protein very, very amphipathic. That means it has distinct surface hydrophobicity and hydrophilicity clusters, making them what? Natural emulsifiers. So very surface active. Okay. All right. So now we're going to take each casein and understand the general structural characteristics. Alpha S1 has 7 to 8 phosphate groups. You don't have to remember 7 to 8. It's not the most phosphorylated and not the least phosphorylated. So it's in the middle. The most phosphorylated is alpha S2, and the least phosphorylated is beta casein. It has a cluster. This is, let's say, it's amino acid sequence, all opened up. Obviously, it's not like the rod, but it's just to demonstrate. So it has the white regions are hydrophobic. So it has 3 hydrophobic regions or clusters, and it has a cluster that is mostly negatively charged with a net charge of -20. This gray region over here, the solid gray, is just a hydrophilic region, but not necessarily charged. Okay, so this is just a visual of the distribution of amino acids within FS. Okay, that's what you want to know. You don't have to remember how many residues or what are the sequences of these clusters or the number of phosphate. You want to Remember that it is phosphorylated, not the least, not the most among the other caseins. And it has 3 hydrophobic regions and 1 electronegative region. Okay, in terms of alpha S2, you don't have to remember 10 to 13, but it's the most phosphorylated among the caseins. Alpha S1, alpha S2, and beta. Alpha S2 is the most phosphorylated. It's very sensitive to calcium compared to the others, given the fact that it's more phosphorylated. It has a region that is hydrophobic on the carboxylic end of the peptide or the polypeptide. Has several clusters, 3 clusters that are negatively charged. So the net charge varies based on the variant, but it goes between -12 to -17. Okay, it has another hydrophobic region here, but most of the hydrophobicity comes on that end, on the carboxylic end. Now, what's unique about alpha S2, it has 1 SS linkage. So 2 cysteine residues involved in intramolecular disulfide linkage. But having this SS linkage allows that protein to take part in disulfide interchange. Okay, one of you asked me about what do I mean by disulfide interchange? Do you all know, or who can define when I say disulfide interchange? I say sometimes disulfide linkages, sometimes I say intermolecular, intramolecular disulfide bond. When I say interchange, what do I mean?
And disulfide that essential change between different molecules.
Yes, it changes. Let me visualize, make that visual for you, because I just want you to understand when I say interchange, it takes part in disulfide interchange. So sometimes you have S here linkage, that is intramolecular disulfide. And then another molecule here has another SS here, but might have an SH group that is free sulfide group. Always to initiate an interchange, you need a reduced SH group, because this will act as a reducing agent. Cysteine acts as a reducing agent, so it will break that bond, and then you will have, this will unfold potentially when you break that SS, and then you will have SH here, SH there, and then now you have a free SH group and another free SH group, then you will form an SS linkage, intramolecular molecule with another molecule. So intra, and this causes an interchange. So change, we just change the SS from the original SS linkage to another. Sometimes the interchange can be within the molecule or across the molecule. So when you hear the word interchange, so the SS linkages are interchanging, changing from being the way it was in the native form. Okay. All right. So since this alpha S2 has SS linkage, that means it can be involved in disulfide linkage. So it is alpha S1 doesn't have cysteine, beta casein doesn't have cysteine, alpha S2 has cysteine, and kappa casein also have cysteine SS linkage. So the beta casein is the most hydrophobic. So if you look at the region, the carboxylic end, it is almost 2/3 the entire molecule. And it has less charge than the others, so it's mostly hydrophobic. But if you can see, like half of it, not half of it, 2/3 is hydrophobic and this one and is hydrophilic. So it's very, very amphipathic. So, yes, very amphipathic. That means we have really condensed clusters of hydrophobic. It has the most proline content compared to the other caseins and the other caseins. Therefore, it has a very, really open structure, random oil. And it's very susceptible to plasmin hydrolysis. Plasmin is similar to trypsin in its specificity. It cuts after a lysine and after an arginine. So there are three peptides location that the plasmin can break. So you end up having the three gamma peptides that I showed you in that flow diagram earlier, and they are hydrophobic because they are in this region, and they stay with the casein if we are separating casein. And then the hydrophilic portion called the protease spectrum remains with the weight after plasmin hydrolysis. You can interrupt with questions, don't forget that. All right, kappa casein, it's also very amphipathic as well. But in this case, the amine group, amine side, N-terminus, is the hydrophobic, and a small portion on the carboxylic end is the. It's not phosphorylated, it is glycosylated. Well, it does have one phosphosyrate. So one serine group is phosphorylated. So it's not really sensitive to calcium as much. But a lot of its thymine is glycosylated. So the thymine residues are glycosylated by different carbohydrates. You don't have to remember what they are, but it's glycosylated, giving it this like tail. This tail end is very hydrophilic, and that is what causes stability to the casein micelle. The size of the casein micelle is directly proportional to the concentration of kappa casein. The more kappa casein is present in milk, do you think your micelle will be smaller or bigger? Smaller, yeah, because they are on the surface mostly of the casein micelle. The more kappa casein I have, the smaller the diameter of the casein is. Yeah. This is a summary where you can visualize the differences between the alpha S1, alpha S2, beta, and kappa casein. So it's just a good study visual for you guys. Okay. So the caseins associate as micelles because of the high relative hydrophobicity, the open structure, the high hydrophobicity on the surface, so they don't like water, so they associate with each other to form a micelle. The micelle is mostly protein with a lot of the salt if the milk resides in the casein micelle, especially the calcium. So 6 to 8% of the micelle is milk salt. Usually the ratio of alpha S1 to alpha S2 to beta to kappa is 3 to 1, 3 to 1. But this is the average, but you can have a little bit of slight differences depending on the milk. And that's why the range in diameter is quite large, 50 to 500, but it really depends a lot on the concentration of the kappa. It's very porous, very hydrated, light scattered. So that means It gives the milk the white color. Remember, cheese are not naturally yellow. The curd is white. Okay, so there are a lot of different models of casein micelle structure. So there is the coat and core model, in each is suggested by these two guys. So that this model states that kappa casein is on the surface and all of the other caseins are in the center. That's what that means. And then there is a subunit model, I'll show it to you. And then there's the nanocluster model, which is what called, it should be factor H. This guy here proposed this model, and it's the most approved model now, and most believed to be true, the nanocluster model. Okay, so we'll talk about very briefly about the cold core model. So the core is only made up of alpha and beta, and on the surface only kappa casein. So that was a simple model saying that all the caseins are the hydrophobic ones are mostly in the middle, and then only the hydrophilic tail of the kappa casein is on the surface. And the last point is true. That is the size of the micelle is proportional to kappa casein. No matter what model we're considering, this last point remains true. Okay, so the submicelle model, which kind of dominated for a long period of time, is that we have submicelles. So each of these circles is a micelle, a smaller micelle, where you have the core is hydrophobic, alpha S1, alpha S2, and beta, and the kappa is around that subunit. But submicelles that have a lot of kappa dominates the surface. So in the middle, you might have some kappa casein, but not a lot. So you will have submicelles. The submicelles with more kappa casein will be on the surface. So the blue dots are the calcium phosphate clusters. So these, okay, what convinced the folks that came up with this model that we have submicelles is this image, the electron microscopy image, and they saw this is the casein micelle, and they saw a lot of like little drops, and they thought, oh, this could be the submicelle. But later on, I'll show you another image that does not necessarily mean that these are submicelles. But anyway, this theory was confirmed or believed based on this visualization. Okay, so it's a lot of stories here, but so this is another visualization where the black dots is mostly your kappa casein molecules, and those circular little drops are the phosphate groups. And then you can see that the interior submicelles are linked by this calcium phosphate bridges or clusters. So here is a bigger visual where you see that the serine molecules of your caseins are phosphorylated, and then they form clusters of bigger molecules of calcium phosphates, and link to adjacent protein, casein, and they form this bridge. So that keeps those submicelles together, glued together. So you have hydrophobic interaction, but a lot of the ionic interactions due to the calcium phosphate bridges that keeps those micelles together or submicelles together And the micelle with more kappa casein was on the outside. So the nanocluster model said, okay, all of this is great, but really we don't have submicelles. What we have is a network of casein molecules associated with hydrophobic interactions. We have a lot of hydrophobicity on the surface. So they associate with hydrophobic interaction. And these dots are the calcium phosphate bridges. So they're linked by the clusters of calcium phosphate. And then while there is some kappa casein in the middle, most of the kappa casein is on the surface due to that glycomacropeptide or the tail of the kappa casein that is glycosylated. So it would be mostly on the surface. That does not exclude it from being somewhere also in the middle, but mostly on the surface with hair-like hydrophilic negatively charged segment that stabilizes the whole micelle in the milk. So this is a visual again of the different models drawn by different scientists, but the last one here is the one by Holt, and that's the most recognized as true. So that's another visual.
And what's the hair-like layer?
Yeah, the hair-like piece at the top. So I want to go back a little bit, and kappa casein is hydrophobic, and the tail end of it is glycosylated. So that tail end of it is the one that would be mostly on the outside, stabilizing the casein micelle because of its negative charge and because it's glycosylated. So this is also called glycomacropeptide when rennet breaks, it breaks here. So that little tail that is hydrophilic is called glycomacropeptide, and that stays with the whey portion, which is very hydrophilic. So when we produce whey protein isolated membrane filtration, we'll see glycomacropeptide among the whey proteins, which is not really a whey protein, comes from the casein. Does that answer the question?
Yeah, I also just don't like that name. It's so weird.
The which one?
The hairy portion.
It's the hairy portion. It has always been referred to as hair-like. I don't know why they do that. What should we call it? The glycosidic arm? The negatively charged arm? What? That's worse?
I don't.
The arm.
The arm. I don't know why they call it that, because the way they draw it, they draw it like the little hairs.
Yeah.
Shooting shade, that's even worse. No matter what we call it, it's not gonna sound good, so let's move on. Okay, so this is the imaging again of electron microscopy that said, okay, so these dots, dark dots, does not mean submicelle. They are your calcium phosphate clusters. So because of those clusters being large and they are linking these caseins to each other, they look a little darker in that scan. So kind of like this is what convinced others that, yeah, the nanocluster might be the most logical description. So this is, I like these images. I think I just giving you more and more images, because every time I read about this, I find an image and I go, oh, that looks so cool. Okay, so this image right here, I like the color because the alpha S1 and alpha S2 and beta, the hydrophobic components of those are orange. And then the gray spheres is the calcium phosphate clusters. And then, the hairy part is the, black. So that would be the, I call it glycomacropeptide here, they call it casino macropeptide, I don't know why, but it should be called glycomacropeptide. And the green is the para-kappa casein, which is the hydrophobic component of the casein. So para-kappa casein is the hydrophobic component. You see it's associated with the hydrophobic components of the other caseins. And then the black structure is your glycomacropeptide. The blue is the hydrophobically bound. Yeah. Oh, so the blue component is your beta casein that's hydrophobically bound, but also this one would leach out under refrigerated conditions. Okay, I like colors. I think that it, helps understand the casein in my cell. So the heat stability of the casein in my cell is tricky. A lot of things happen when you heat, but really it is stable at really high temperature. However, extensive heating will lead to coagulation. Now, many things happen that cause destabilization due to heat. We get denaturation of whey protein. I'll show you like the diagram in a little bit. We have many things happen. Denaturation of whey protein, obviously, will denature, unfold. You have a reactive SH group. It will have an interchange between kappa casein and whey protein. So it enhances the formation of large aggregates between whey protein and casein, especially kappa casein and sometimes alpha SP. We see a decrease in pH, and I will show you why in a little bit. Why we have a decrease in pH. There's so many reasons that result in decrease in pH. I'll show you the next. We form something called colloidal calcium phosphate. So at high temperature, calcium phosphate within the micelle leaches out and changes the balance of free calcium and free phosphate. And you form a big colloid of calcium phosphate outside of the casein. And by forming big colloids, the phosphates lose hydrogens. And when they lose hydrogen, because they're binding with calcium, because there are three negative charges on the phosphate, and each can bind with calcium and form these big colloidal systems. And every time the calcium binds, the phosphate loses the hydrogen. And when a hydrogen or proton is lost, pH decreases. So we form this calcium phosphate, we reduce the pH in the process, we shift the balance of free calcium and free phosphate in the system. We can get dephosphorylation of casein. We also get degradation for lactose. It beats me why I have it in different color. I try to remember, but I couldn't. Why? What did I want to say here? I don't know. Kappa casein can hydrolyze at high temperature, and then we lose on the zeta potential. With high temperature, the charge on the surface will decrease. And then this all contribute to increase in hydrophobicity of the micelle. If we reduce the phosphorylation, hydrolyze the kappa casein, change the balance of calcium phosphate within the micelle, all that leads to increased hydrophobicity and new interactions of different casein micelles with each other, leading to coagulation. Okay, so this is the diagram that might explain everything that I talked about. So with high heat, we increase the colloidal calcium phosphate. So we form big clusters of calcium phosphate. So that causes a decrease in pH. This leads to destabilization of the casein micelle
because we changed the balance of calcium phosphate within the micelle itself. Degradation of lactose also cause decrease in pH. Breakdown of dephosphorylation causes a decrease in pH, and we get the decrease in pH, we get reduced zeta potential, so the net negative charge will be lower as we come close to the isoelectric point of the casein. So we will get new interactions that could happen if we have colloidal systems outside of the casein micelle. Then we might have calcium phosphate bridges between different micelles, bringing them together and causing aggregation. So this new system here causing casein micelles to interact with each other, reducing the zeta potential on the surface, all causes aggregation, which can be irreversible, especially if we have interaction of denatured beta-lactic globulin with kappa casein that will enhance the aggregation via disulfide interchange. So that ultimately, with high heat, a lot of things happen, but the final thing is irreversible. A lot of things go on that leads, it's not a simple protein denaturation and then polymerization. In casein micelle, given the complexity of the micelle, a lot of things happen, contributing to the aggregation. Yeah, mostly via hydrophobic interaction and intercasein calcium phosphate bridges. Intercasein micelle calcium phosphate. All right, you can have a 5 minutes break. Between the micelles rather than inside of them. So like different micelles, because the colloidal calcium phosphate will be mostly in the wave. Because then in the wave fraction, so outside of the casein. And then that's when the interaction of the this one over here. Yeah, this is another something, not related to this. This beta-lactic globulin is denatured. This one has SS linkage. Beta-lactic globulin has a 3S stage, then interaction. So there are different things happening leading to this. There are different things contributing to the end patterning of the.
For participation, they were just wondering, do you want to keep going, or is the 1% done?
No, it's nice. Okay. Next person is Ellen. Then,
So,
yeah.
maybe we can print another one here for all.
Yeah, yeah, I will drink another one. Would be good to like send me an email right before class on Monday or something, just to remind me. Yeah, but this time I didn't make a mistake. Okay. We'll do 20 minutes of this and then hand off to our presenters today. Okay. So also casein micelles are impacted by the pH, so acidity. So the isoelectric point is around 4.6. So when we are making yogurt, we reduce the pH by having a culture that convert lactose into lactic acid, and the pH gets reduced to 4.6, and then the net charge is lowered down to 0 potentially, and with that we get the casein micelle. We lose the repulsion that we originally had to the glycomacropeptide of the kappa casein. Then the proteins, the caseins come together and we see minimal synthasis. So we kind of form a gel-like structure holding the water, and that's your yogurt. However, with enzymes, this destabilization is a different process. We have the mannate enzyme or the chymosin enzyme that specifically break the bond, releasing the glycomacropeptide from the para-kappa casein. And when we release that, then we have the casein micelle kind of fused together rather due to hydrophobic interactions and calcium phosphate bridges. And then the way is separated. So there is syneresis, so the curd come together and you get the whey protein or whey with the whey protein
and the glycomacropeptide separate from the curd. We enhance the calcium phosphate bridges formation by adding calcium. However, one thing is negatively impact the formation is the presence of denatured beta-lactoglobin. What happens there if we're trying to make milk from curd from a pasteurized milk at high temperature, 70 or above, what happens is we have denatured beta-lactoglobin in there, whey protein denatures at 60 to 70 degrees, slightly above 70 degrees. So the denatured beta-lactoglobin is going to interact with the kappa casein via disulfide linkage. That interaction is going to hinder the enzyme. The rennet enzyme and chymosin will not recognize the binding site if we have denatured beta-lactoglobin attached to the kappa casein. So that is not desirable. So often the milk is heated to like 60 degrees or so, not really above 70 degrees if we are intending to make a cheese out of that milk. So this is another nice illustration, colorful, but it kind of in A is your micelle, the stabilized micelle, where we have the kappa casein, not the kappa, yeah, now I don't want to say the hairy light because he just didn't like that. What do I say? The glycated chain is on the outside, and then the micelles are not interacting, stabilized. Now, on this side, I have, you don't see the glycomacropeptide, it got hydrolyzed, so that's cheese formation. Then we have interaction via hydrophobic interaction and also calcium bridges. Now, in C, that's in yogurt formation. So here we have your glycomacropeptide is no charge, no net charge anymore. And then we get the interaction via hydrophobic interaction and entrapment of water. Here is the two cases. One time we want the interaction with the casein and whey protein. This is the whey protein, those blue circular structures. Sometimes we don't want them. If we have the blue protein or the beta-lactoglobin interacting with the kappa casein, the enzyme will not recognize the site, will be hindering cheese formation. But sometimes whey protein is added to yogurt to enhance gelation by this formation of protein. So it is good in one way, but it's not good in another. So when we want to make a cheese, we don't want that with enzymes. We don't want that to happen. When we are forming a yogurt, we might add whey protein to enhance the gel strength of that yogurt and reduce syneresis. Okay, storage. So during storage of milk, we get what we call age gelation. And this is mostly induced by the endogenous enzyme plasmid. It causes this plasmid and also bacterial proteases. So even non-pathogenic bacteria, even pasteurized milk have non-pathogenic bacteria that can release proteases, both plasmid and these proteases cause breakdown of the beta casein, mostly causing this thinning first and gelling of the milk. Also, we have interaction with whey protein, also that causes gelling if the whey protein is denatured in pasteurized milk. And then we have overall reduced surface charge with aging, and that causes more gelation over time. All right, any questions about casein before moving on to whey protein? You all know it very well now. Okay. So next week, you're going to come up with words other than hairy for the glycomacropeptide. So you will get +1, whoever has the best name for the hairy structures. Okay, that's your assignment. Plus, there is a practice problem set 4 that you can start working on. Okay. Whey proteins. We love whey proteins, don't we? Okay, so whey proteins represent, like I said, 20% of the total protein. The functional proteins that we care about is beta-lactoglobulin and alpha-lactalbumin. So, and mostly beta-lactoglobulin is dominant, so 23 times more than alpha-lactalbumin in concentration. So usually they exist in molecular dispersion, so either a monomer, a dimer, or an octamer. So they don't necessarily form a quaternary structure, a true quaternary structure. They're mostly monomers or dimers. Octamers are produced when the pH is close to the isoelectric point. So we've seen alpha-lactalbumin before. Alpha-lactalbumin has mostly alpha helix structures. One strand has beta sheet structure. We have a lot of SS linkages, about 18 residues. So we have 4 SS linkages. We don't have a free sulfide group. Beta-lactoglobulin has 5 cysteine residues, so this gives us 2 disulfide linkages, one here and one there, and then 1 free SH, mostly active and problematic, is having this free SH that kind of is the trigger for disulfide interchange. So they're both highly structured globular structures. So you have a lot of, here you have a lot of beta sheet in beta-lactoglobulin, 1 alpha helix, some beta turns, not a lot of random coil. So it's very ordered, structured globular proteins. If you remember, more alpha helices denature at lower temperature, and beta sheet has higher stability, so the structure denatures at 73 degrees Celsius. So this is a visual of beta-lactoglobulin per se. So this is a colorful visual, and this is illustration of hydrophobicity on the surface. So we talked about how before that beta-lactoglobulin is mostly hydrophilic on the surface, having one region that is hydrophobic. So mostly hydrophilic with one clearly pouch that is hydrophobic on the surface. You might see some hydrophobicity, small residues here and there, but it's mostly hydrophilic with one concentrated area of hydrophobicity on that surface of whey protein. So we did talk about the first 3, 4, 5 points. And this is because of the surface hydrophilicity and minimal surface hydrophobicity. We talked about solubility of whey protein, mostly soluble at all pHs, including the isoelectric point, because of the high hydrophilicity on the surface. Even when we don't have net charge, 0 net charge, we have low attraction via hydrophobic interactions. So the protein remains solid. However, when you denature it, you lose charge and the protein is open. You have a lot of hydrophobicity exposed. At 0 net charge, we have low solubility. So this kind of brings you back to the structure function relationship of whey protein. So it denatures above 73 degrees Celsius. It plays a role in when interacting with kappa casein, causing H generation or slowing enzymatic hydrolysis by chymosis. So 2 not very good things, but the good thing that I didn't add here is adding it to yogurt. It actually is a good thing. So the disulfide interaction with kappa casein for yogurt application is desirable. Sometimes they add whey protein to yogurt. But the bad things is age dilation and interfering with the chymosin hydrolysis. So the stability is pH dependent, obviously, so it is most sensitive to heat or destabilization around pH 4 to 5 really. Maximum stability between pH 6 and 7, actually, not just pH 6. And then we lose stability after pH 8.5. So at high alkalinity, we have internal repulsion within the protein due to like charges, and it opens. So this is a demonstration of what happens at different pHs. So the protein is monomer, whey protein, or beta-lactoglobulin, is a monomer at very low pH and very high. So it exists as monomer. Between pH 6.5 to 7.5, or around 5.5 to 7.5, they exist in diamond. And that is in milk, is the pH in that range, so they exist in diamond. So whenever we are around neutral, the whey protein is in diamond. If you're running size exclusion chromatography at neutral pH, you will get a peak that is equivalent to 2 molecular weight of beta-lactoglobulin if you're running it in phosphate in buffer. That's because it exists in diamond. Now, around the isoelectric point, it exists in octamer because you have the least charges, so you will have more polymer interactions, and with heat, that octamer grows obviously and lose solubility around the isoelectric. Now, above pH 8.5, what happens is that monomer is going to have internal repulsion, and that will be an expanded, that is an open structure monomer, and that causes irreversible at high. Alpha-lactalbumin, again, we talked about having alpha helices, more than beta sheets, one beta sheet, 4 cysteine, or no, 8 cysteine residues and 4 cysteines. That means we have 4 disulfide linkages. We don't have a free sulfide group. Again, compact structure. It's a calcium metalloprotein. That means it forms interaction with the divalent ion calcium, causes the more calcium there is, the more stability there is against denaturation of alpha-lactalbumin. It has a physiological function. It enhances or regulates the synthesis of lactose. It is more heat sensitive than beta-lactoglobulin due to alpha helices. Sometimes thermal denaturation is reversible if you have just alpha helix, alpha lactalbumin in solution. You don't have beta lactoglobulin. So you don't have the 3SH group that is disastrous for disulfide. So if you only have alpha lactalbumin and you heat it, and then you, for a short period of time, then it could be reversible. You don't form those large polymers via disulfide interchange, because you don't have that catalyst of the cysteine group. Presence of calcium helps with stability, but at low acidity of the milk, we start losing calcium, start dissociate and becomes more soluble in water, and then you lose some of that stability that is caused by holding on to the divalent atom molecules. Okay, So this is a summary table and we don't need to memorize anything, but it kind of puts beta-lactoglobin, beta-lactoglobin, alpha-lactoglobin, all the caseins, how they differ in molecular weight and secondary structure in thiol, in phosphate groups. But what I want you to know is this table, which we are going to fill it together. All right. So how is the amino acid distribution differ in casein and in? So when I say amino acid distribution, I'm talking mostly about cluster of hydrophobicity and clusters of hydrophilic. How are these two different? You know this. Huh?
Being more hydrophilic than like because that's like it seems to get.
So on the surface, yeah, but what did we say about casein being natural emulsifier? Why is it natural? Very amplified, right? So it has the amino acids are really in clusters. So highly amplified. However, in a way, you have regular distribution. Hydrophobic amino acid, hydrophilic amino acid, you don't have really a lot of clusters and separation like we have in casein. All right. So in terms of molecular structure, configuration, conformation is yes, open structure, and the way proteins are globular. Yeah, there you go. See, you know this. Open, random, little secondary and tertiary structures, whereas in way we have globular compact structure. Okay, what about heat stability and dilation?
Casein is more stable.
Casein is more heat stable, yes. So what causes dilation in casein? Or yeah, what external factors cause dilation? Let me relieve you, we're getting to the end. So we have age, dilation, and over time, a lot of things happening. We have acid gelation due to pH to the isoelectric point, and then we have the enzyme breaking down of the glycogen peptide and enhancing casein-based micellary. Whereas in whey, we heat it, we nature it, we induce thermally induced generation. All right, what about association? So how do the casein associate? Yeah, so we're forming what? Micelles. Whereas whey, no, we form dimers, monomers, octamers, whereas casein form more organized quaternary structures. These are called micelles. So you want to understand the micelle formation and how the casein micelles associate, casein molecules associate to form a micelle. Sensitivity to enzymatic hydrolysis, which would be more sensitive to enzyme hydrolysis? Casein, open structure, sensitive to enzyme digestion in our gut, also sensitive to rennet digestion with chymosin, whereas whey is a globular protein, it's not denatured, it resists hydrolysis. Okay. What about surface absorption and emulsification? Which one is better? Casein. So what do I need to do to whey protein to make it function as an emulsifier? I want to denature it a little bit. I might want to break some of the disulfide linkages, reduce it so that it opens up, it's more flexible, and it can go to the interface easily. Okay. Solubility. It's higher. Casein is better in solubility? Whey is better. So it precipitates at pH 4.6, whereas whey protein is very soluble at low pH, and it has very good solubility across pH, except when it is DH. Right? A conjugation. That meaning, think about homo protein versus heterogeneous versus homogeneous in terms of other groups than amino acids. What do we have other than what makes it interact with calcium? Phosphate. So it's phosphorylated and glycosylated. Phosphorylated, glycosylated whey protein doesn't have any post-translational conjugation. So there is no additional groups conjugated to it. Sulfur residues, how are they different? Do we have a lot of sulfur residues in casein? No. Only kappa casein has one SS linkage, and alpha S2 has one SS linkage. However, there is a lot of sulfhydryl groups, sulfur groups in whey. Only whey protein, beta-lactoglobulin has a 3SH group, which is the culprit of a lot of things, but sometimes good, sometimes not good, and have a lot of SS linkages. However, casein has mostly methionine and only one SS in kappa and one SS in alpha. Okay, so I think that's a good stuff. We will hand the floor. Yes.
Might have already mentioned this, but what exactly do you mean by post-translational modification?
Post-translational modification. Okay, so what causes protein formation in cells? What triggers protein formation in cells?
Transcription.
Yeah, transcription. So you have the DNA material, and then you have the RNA, and then you have the synthesis of the protein. After the synthesis of the protein, another reaction can happen that causes phosphorylated blood. So in the cell, so in the milk before the milk is taken out of the cup. Okay, yeah. Good. That's a good question. Good job. Okay, so I'm gonna stop here and we're gonna pass. This time I come prepared. All right, so take one and pass. Before these guys start, I just want to remind you to please prepare at least one question. They need to answer questions and you guys need to pay attention. So that's the only way. Prepare a question. And I might call on people that I didn't hear them ask question last time. Don't make me do that.
Our presentation is full.
Your presentation is cool? Guaranteed. So pay attention. I asked Anastasia if you made any changes. Did you? After you
At like 10 a.m. or something.
so, but when you sent it to me, it was before or after?
It was before, but it's also, we sent you the shared link.
Do you want me to go to the shared link just to be on the safe side?
That'd be awesome.
Sure. Yeah, I'll do that.
Okay.
So,
Or just like be talking through it and you take a couple of edits. Changing slides.
okay. Thank you. Yeah. And do you want me to download it into PowerPoint for presenting, or do you want to present from slideshow here? Which one?
Just the slideshow.
Okay, let me just.
It's like Google Slides.
I don't know how to translate to PowerPoint.
Yeah. All right, so, but this way you won't see your notes. You want to see your notes?
I don't have this.
I don't know, I only have like
Okay, so,
little things on that.
Can we?
this is how it's gonna be. You're not gonna see,
Can we do same screen then maybe?
you wanna change my setting?
No,
Please
that's
don't
okay,
do
that's
that.
okay, I won't.
I can make it into PowerPoint.
You can, okay, sure.
Should I make it into
Okay.
PowerPoint? Okay.
If you insist.
If I insist, if you insist. Okay. Did we all get one? Do we have enough or we ran out?
Do we have enough?
Did you have enough or you ran out? Wow, did I just give you just enough for everybody? Okay, these are for you guys, for later. Evaluate yourself, your partners, and then write your name at the bottom. Okay. Let me sit down. Chris is on Zoom.
All right, are we ready?
No.
Yeah.
Wait. Okay. You have 20 minutes. You can get started.
All right, hello, everybody. My name is Alyssa Snowchenko.
I'm Anastasia.
And we're gonna be talking about the characterization and deactivation of polyphenol oxidase in blueberries. So just a little quick overview. So polyphenol oxidase is an enzyme that does cause a lot of degradative and sensory effects on fruit. So for example, color changes, softer fruit, nutritional loss, also some sensory attributes, like it tastes a little bit weird. And just in general, spoilage, like we don't like polyphenol oxidase. And the rate of polyphenol oxidase activity can be influenced by a lot of factors, including pH, temperature, and pressure. However, using these can also lead to degradatory effects on fruit. So for example, if you use a really high temperature, sure, you're going to inactivate polyphenol oxidase, but you're also going to end up cooking your fruit, which is not great. So polyphenol oxidase reacts with phenol. And so quick pop quiz for you guys. Can anybody tell me what this amino acid is?
Yes.
Yes, tyrosine. You guys got it. Okay. Plus 1 point. Plus 2. I don't know. But it can also react with other phenols and diphenols as well. So for example, dopamine, D-L-DOPA, or methyl catechol. And another quick fun fact that I found out is that tyrosine is actually a precursor to dopamine. So eat stuff with tyrosine in it, maybe. So Pamela went over this also. She kind of went over it before we did, but that's okay. This is the reaction of polyphenol oxidase with phenol. So initially we see the what?
You said she went over.
Oh, you did. You had this exact
On
same
Monday.
image. Yeah.
I was like, Pam, I spoiled it.
Yeah. Oh, sorry.
Okay, minus.
For the time limit. Okay. So first of all, the phenol goes through hydroxylation into a diphenol. And for this entire reaction, oxygen also has to be present. And then afterwards, the diphenols are oxidized into oquinones, and then they go through a further reaction with a lot of other things to form complex brown polymers. And then another quick overview. So Km is the substrate concentration necessary for half of the maximum rate of reaction. And then Vmax is just the maximum rate of reaction. And you'll see these values later on in the presentation as well. And then blueberries, why blueberries? So they have a high concentration of polyphenols, and while 60% of the crop is sold as fresh, The rest of it is further processed. So when it's processed, it is more broken down, juiced, and introduced into oxygen. And this polyphenol oxidase can react more quickly in those instances as well. However, there is still issues with fresh blueberries and polyphenol oxidase too. So the first paper that we're actually going to talk about both papers at the same time, but one of the papers we're talking about is Siddiq and Dalan. And their objective in the paper was to characterize polyphenol oxidase, which is again the enzyme responsible for a lot of degradatory effects in blueberries, and to understand the best ways to inhibit or inactivate it. And the application is mostly, again, for processed blueberries, however, maybe some application with fresh blueberries as well.
And the second paper that we will be talking about will be by Tracy et al. The objective of this paper, there's two main objectives, which is to determine blueberry polyphenol oxidase kinetics, substrate specificity, optimal pH and temperature, as well as pressure. And the second objective is to investigate inactivation of blueberry polyphenol oxidase through heat and chemical inhibitors. They only use SDS in this, which is a detergent. And some applications is pretty much also similar to the first paper. It's more so towards processing and more specifically just preventing discoloration and degradation during processing.
So we're going to go over the extractions and assays performed. So first of all, both papers had a similar extraction process. They both took high bush blueberry samples and they were blended in a buffer, either phosphate or trisma. And then the sample for Sidon and Dalan, the sample was filtered through a nylon cloth and the juice was kept.
That is something that is so wrong.
Oh, sorry.
Yeah.
Okay. And then for Terrafi, they centrifuged the sample. So the supernatant was kept, but the pellet was discarded. And then afterwards, that supernatant and juice was kept and then precipitated. For Siddiq, it was precipitated at a low temperature with acetone and then filtered again. And then for Terrafi, it was precipitated with ammonium sulfate. And then that precipitate was resuspended for both of them in a buffer. And then for Siddiq, they, to again get that pure, partially purified polyphenol oxidase, they centrifuged and refiltered, while for Terrafi, they just did dialysis. And then for both of them, the result was a partially purified polyphenol oxidase. And so the assays we're going to be going over, both studies went over polyphenol oxidase activity and kinetics, optimal pH, and thermal inactivation. Siddiq and Dalan specifically focused on optimal temperature, substrate specificity, and polyphenol oxidase inhibition, including chemical inhibition and also storage stability.
And Tracy et al. Paper mainly focuses on the effects of detergent on polyphenol oxidase activity. They also had just thermal stability and also the combination of high pressure and thermal treatments, which affects the stability and activation and inactivation of the polyphenol oxidase enzyme.
And now moving on to results and discussion. So for Siddiq, and yeah, go ahead. For Siddiq and Dalan, their optimal pH temperature was 6.1 and 6.3, and this was determined using two different buffers, sodium phosphate and citrate phosphates. However, they did mention that other papers found a different pH optimal for this enzyme.
In Tracy et al.'s paper, they used McIlvaine buffer, which I found out is just a fancier way to say citrate phosphate buffer. And their optimal pH was 5.5. So I think it's really interesting to see how different varieties of blueberries, I think that's what their paper cited, just has like different optimal pHs. And there was no graph or anything reported from my paper. Boo. Yeah. And then we'll move on to enzyme kinetics. So Siddiq and Dalan, they have a both papers use catechol as an optimal substrate, and the second.
And again, because they determined the optimal pH was 6.3 for their blueberries, that's what they used. They found a Km value of 0.015 molar, which is pretty low, and a Vmax of 2.57.
In contrast, Tracy et al.'s paper also used catechol as a substrate at the optimum pH 5.5, but a much higher concentration was required to reach Km at 0.22. And the Vmax was also much lower at 0.654. And so, oh my gosh, the formatting, no. So the enzyme from CDIC's article was more potent initially, whereas the enzyme in Trafi et al.'s paper was less potent initially.
And we use the word initially because further on, you'll see the activity kind of changes between the two of them.
With the, downloading PowerPoint was uploaded format.
Yeah, I think so.
Yeah, because that was supposed to be like right there.
Uh-huh.
And it's okay. Okay. Google Sites, it's weird.
Yeah. So for the optimal temperature for acidic in Milan, again, it was determined at pH 6.3, and it was measured after 1 minute. So they didn't hold it at that temperature, they kind of got to that temperature and then determined activity. And their optimal was at 35 degrees Celsius, and then they see a continuous decrease in activity with increasing temperatures afterward. So for example, at 70 degrees Celsius, it had 35% of initial activity. For inactivation, pseudokinolones saw continuous inactivation at temperatures of 55 to 85 degrees Celsius. So they didn't have any latent polyphenol oxidases, which we'll talk about more soon.
And in contrast, Trafi et al. Kind of divided it into two graphs to see the trends. And in the lower temperatures, there is a lot more activation compared to deactivation. Whereas over 72 degrees Celsius, they notice a lot more inactivation. And pretty much the authors kind of theorized that the latent polyphenol oxidases were activated upon this temperature increase over time. And continuing on with some kinetics modeling, honestly, I'm not super sure if I fully understand this. But I'll try my best. And the activity is determined by the amount of latent polyphenol oxidase, which is Ka, and the active polyphenol oxidase denaturing, which is K. So K will be kind of used by the authors as a denatured constant. And I also don't really know what this equation is about, but it was pretty much just kind of talking about the reaction steps that's present in the enzyme, and it's going to assume that all the steps are they all go forward, they're not reversible or anything. But some of the values that I like you guys to focus on, which is AO, A, and this is not A10, this is AL0, which is pretty much just the concentrations of active enzymes and latent enzymes at different time points of the graphs that we will show in a little bit. So for thermal stability, the highest peak of activity was seen at 70 degrees during the 10-minute treatment. Okay, the increase in activity could be caused by some activation of latent polyphenol oxidases, pretty much just those minor changes in conformation allows for more active sites to be exposed and allowing for an increase in relative activity. And irreversible activation was observed in this reaction. Pretty much what the authors did was they pre-treated the enzyme for 5 minutes at 70 degrees, and then they continued, they stored that sample overnight, and then they decided to run with the 10-minute treatment. And pretty much what they found was that it still reacted. So they concluded that this activation of the enzyme is irreversible. And the effect of SDS on polyphenol oxidase activity, I had to pull this graph out from like supplementary materials, so I hope that's okay. And because they mentioned that there is a 9.2 times increase in polyphenol oxidase, even with like a very minor concentration of SDS. And it was stated in the paper, but I had to see the graph to believe it. So And pretty much what the authors think happened was that, again, there is some limited conformational change in the proteins, allowing for more active sites to be exposed and pretty much causing activation of latent polyphenol oxidases. And through this minor experiment in the paper, the authors concluded that there is a presence and activation of latent polyphenol oxidases. Yep. Yes.
And then moving on to storage stability. So Sadiq and Milan determined storage stability between a frozen, refrigerated, and room temperature samples after between 4 to 20 weeks. However, they didn't really show all of their data. They only gave us 3 data points. So they told us that at frozen temperatures, the polyphenol oxidase retained 80% of its activity after 20 weeks. And then for refrigerated samples, it only retains 10% of activity after 20 weeks. And then for room temperature, it lost complete activity in 3 weeks. However, I feel like the refrigerated room temperature isn't really useful because after 20 weeks or 3 weeks at room temperature, your product is going to be spoiled anyway. So it doesn't really help. However, it is nice to know that polyphenol oxidase will be activated or will be active even if it's frozen.
There's no tables or anything.
They also did chemical inhibition, and they found that the benzoic acid series was the least effective. So even at 2 millimolar, they had less than 30% inhibition. And then they found a couple that were more effective. So even at 0.2 millimolar, they saw over 85% inhibition, and at 2 millimolar, they saw over 99% inhibition. And some examples are ascorbic acid or L-cysteine.
Okay, so we're going to come back to a combined treatment of high pressure and heating. So the highest activity increase was observed at the highest pressure, which is 690 megapascals. And in contrast, all of the treatments had complete inactivation at 90 degrees, regardless of pressure. And this is a lot of graphs. I'm sorry in advance, but the highest increase in activity was observed in that graph over there, which is at 40 degrees and 500 megapascals after 20 minutes. And in contrast, the best decrease in activity was at 0.1 megapascals at 80 degrees. So the lowest pressure actually led to the best decrease in activity, which is kind of disappointing, knowing what the authors wanted to do with this paper. And the general trends, there isn't really like a very general trend, but in graphs at higher pressures, a increase was followed by a decrease in polyphenol oxidase activity, and pressure applications at temperatures up to 80 degrees actually stabilized the polyphenol oxidase, making it much more, making it better at resisting that thermal denaturation. And so,
yes, and so kind of to explain this a little bit more, when it's like a latent PPO, what is happening with activation? Essentially, there's conformational changes that happen in the enzyme when it's exposed to SDS, which is a detergent agent, or that high temperature in general, or pressure. And so what they're assuming is that there's a cleavage of the C terminal. So here we have a precursor of polyphenol oxidase, which has the N terminal and C terminal. The latent polyphenol oxidase, which is inactive, doesn't have the N terminal, but still has that C terminal site. So again, with that addition of temperature and stress or environmental changes, that C terminal is cleaved, making your polyphenol oxidase active.
okay, this is a lot of numbers, and pretty much I will try my best to kind of summarize the trends. The authors didn't really point towards like a specific pressure and temperature treatment. They pretty much kind of grouped everything together. But pretty much in these lower temperature that ranges and across all pressure values, enzyme activation was dominant. And in contrast, in these higher temperatures and higher kind of across the pressure treatments, And the only exception for kind of like, between 60 and 72, there was a lot of enzyme inactivation. And lastly, Ka, which is the activation rate constant, increases as pressure increases in the values that are highlighted by the green bars. But I'm not super sure if this is a valid trend, because it's the trend isn't really like, it doesn't really go across everything, but that's what the authors pointed out. And another table with more numbers. This is the last one, I promise. But some trends that were noticed is that this is talking about the inactivation constants. So inactivation constants kept on increasing as temperature increased. And there is a kind of decrease in inactivation as the pressure values went up within this range, and in the higher pressure range, the inactivation constants actually increased. And so moderate pressure at higher temperatures actually prevent enzyme inactivation, and an explanation for it will be shown in the next slide. So at this point, you might be thinking, what the heck is going on, Anastasia? And it's really confusing. It took me a long time to kind of decipher what the authors were trying to get to. But pretty much a complex trend was observed, which is kind of an understatement. It's a really interesting kind of mix of what's happening. And pretty much what the authors kind of concluded was that high pressure has a much higher impact than the temperature treatments. And pretty much like what they attribute to is that pressure can cause changes in protein conformation in both active and latent polyphenol oxidases. So in latent polyphenol oxidases, it can actually open up binding sites, which increases activity, whereas in it might also inactivate some enzymes. So that kind of might explain that weird increase and decrease in activity trend. And the mild pressure induced mild pressure treatments actually allowed for stabilization in the protein structure, and that prevents the eventual thermal inactivation in the proteins. Pretty much what pressure kind of allows for hydrogen bonds to be more stabilized, whereas during thermal treatments, there is a loss of water. So this stabilization might actually prevent the loss of water and allows it to remain active. And we will move on to conclusions.
So for conclusions, we're going to talk about what's best for the activation or activity of polyphenol oxidase. So Siddiq and Milan found that a pH of 6.1, 6.3 is most optimum at 35 degrees Celsius. While Refi found that a pH of 5.5 at 70 degrees Celsius is most optimum. And also one of a really high pressure at 500 megapascals at 40 degrees Celsius. So essentially, these are parameters you want to avoid if you want to limit polyphenol oxidase activity. For activation, however, Siddiq found that at 85 degrees Celsius, at 6.3, at least 95% of the polyphenol oxidase was activated. And for Refi, it was a slightly lower temperature at 78 degrees Celsius. But again, that was at a lower pH as well, so that kind of goes hand in hand. If you have a lower pH, it's usually a lower temperature to nature your enzyme. And then also, they found the best pressure to inactivate polyphenol oxidase is atmospheric pressure, so no pressure at all. Which kind of sucks because the aim of the study was to determine whether using pressure, you could lower the temperature needed to inactivate polyphenol oxidase. However, they found that pressure had the opposite effect, and it actually favors polyphenol oxidase activation and stabilizes it as well. And then a couple of other conclusions. For storage, if blueberries are frozen, polyphenol oxidase will continue to be active upon defrosting. For chemical inhibition, they recommended L-cysteine because it has relatively little sensory effects, but it also is very highly effective in small concentrations. And then lastly, SDOs is not recommended for inhibition, because it can activate those latent enzymes.
Hey, some real world applications. So they did all this research and now what? For Trefe et al.'s paper, they pretty much talked about some problems during high pressure treatment of blueberries, which is really sad, but pretty much what they concluded was that even slight pressure treatments at mild temperatures can cause a lot of polyphenol oxidase activation, which is not good and should be avoided. So their recommendations during processing and storage is to pretty much refrigerate the product and avoid oxygen during that entire process.
And then for Steve and Milan,
Sorry.
essentially when processing blueberries, if you wanted to inactivate polyphenol oxidase, you have the juice, you can take that temperature down, or take that pH down to that 6.1, and feed it to 85 degrees Celsius to fully inactivate your enzyme. And then a couple of critiques. So for Siddiq and Milan, I really like that they address the differences in temperature and pHs reported in other literature. And they also give recommendations for industry. However, a couple of cons, when they were determining the optimal temperature, they don't really address prolonged exposure. So they only tested the activity after 1 minute, not perhaps at 10 minutes, which is what the other article did. And they're also missing a lot of plots, like they didn't have a enzyme kinetics plot. They didn't really show the full data for their storage stability either. So I found that to be a little lacking.
And for Turkey et al.'s paper, I really liked the discussion of kind of potential effects of pressure, heating, and detergents on the polyphenol activity, and that they did some like mathematical equations to like see how the activation and inactivation mechanisms happen. And my kind of critique would be that the mechanism of pressure activating polyphenol oxidase is not well understood. There's no like, I'm sure it's probably changed since 2016, but there's no like paper that really solidifies that, like why pressure might affect polyphenol oxidase. And they sort of mentioned it in the paper in a way that's like, well, general knowledge, we understand that pressure does blah, 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 which doesn't sound very credible. And again, there's no line weaver bird plot. They just kind of gave us a bunch of numbers and ran with it. So yeah. Any questions?
Right, so they are so good job. They're a little bit over the time.
Yeah.
But okay, we'll open it up. Questions? Please ask two questions. Go ahead, and start asking students. Go ahead. You told that the inactivation, polyphenol oxidase activation is staging. One that is reversible and one is irreversible. Am I right?
I don't know if it's actually reversible or not.
I think I'm thinking of-
Oh yeah, so like in
Yeah, I'm pretty sure it was just irreversible is what they found.
yes, it's pretty much like just because they did that pre-treatment and then they stored it overnight and then they still ran the experiment. It's this like line over here, and they still noticed that there is still some activity, and that's how they concluded that it was irreversible. I'm not super sure there's like anything, any like things that they mentioned are reversible. I just kind of noticed that those are reversible.
Actually, I had a question of that. So what does it mean to say irreversible activation? So once the enzyme is activated, what
Right.
would make it unactivated?
I think they were maybe assuming that it was activated with temperature, and when the temperature goes back down, you could reactivate it again. But here you can see it does not activate again. It stays at this general line. I think that's what they were talking about, but
So that doesn't mean irreversible activation.
Yeah,
What do you understand with the word reversible?
again, it
The
doesn't.
previous slide, I think, mentioned the reversible, it is of the formula that you told that in this, yeah, you told that all of them are reversible.
Oh, no, I said, assuming it's, oh,
Assuming it only goes forward, was the kinetics modeling.
I mean, is it necessary to calculate the time of reversible, activation? I mean, for example, it may, be different, from different sources. For example, for apple or carrot or everything, it may vary and I don't know if they mentioned in the society of, calculation of the distance state.
Yeah, I mean. They assumed that the reaction was only forward. They didn't do anything on backwards or reversing it. Yeah. No. Sorry, I can't provide you more information.
So I have a question, and maybe you guys have understand this, but can you tell us how they got elected policy monitors, like?
Right, so that's the interesting thing, because if we go back to the methods, like. Here, right, it seems like they had, both had pretty similar methods of extracting the polyphenol oxidase. And I can't really pick out like what would determine, or what activate some of them or wouldn't. But when we went to,
SDS.
we're gonna go to but we do see, so for acetic and it seems like all of them are active because that Vmax initially was really, really high versus for Truckee, it was very low, which I assume is because some of them are linked and others weren't. Yeah, but maybe it was either the buffer that they used or the fact they used dialysis. I actually think they affected. Yeah, I'm not really sure.
So that brings me back to the question that I had, is that they extracted this design of the.
Yeah.
What the extraction of that protein impacted in the actual very first things.
I assume so, because we see that there is, with temperature. They see that some of them are activated, some are. Some of them are active, so maybe the fact that CBD used a very low temperature potentially. Or use acetone instead of ammonium sulfate precipitate. Maybe some of that had an impact. On. Like,
Yeah, because I asked them, what would we do?
but. I wanna say it would like open it up a little bit.
So, yeah, what, are these the ones that saw less activity? That's.
This one showed the less activity and showed. The blue one. Yeah, but yeah,
That could be the opening up.
yeah, so if it had the most activity, maybe because of the acetone, it opened up all of those latent polyphenol oxidases immediately. Okay.
Right, so that doesn't tell us how the polyphenol oxidase in blueberry would behave. Rather than in the purified form.
Right.
Yeah, so that's definitely a discrepancy.
Yeah, so that another question is when they use, when they said, okay, the recommendation is reducing agents, so reducing agents are not really inhibitors. They're not inhibiting the enzyme, they're reversing the reaction, right? So when we add reducing agents from class, what we learn about the reducing.
Right, that prevents the formation of those.
Yes, reverse
Right.
those, the oxidized forms
Mhm.
are reversed. By being reduced.
Right.
So it's not really inhibiting the enzyme.
Oh. Yeah.
Yeah, reducing agent will not inhibit the enzyme per se, it's just
Right.
reducing oxidized product going back. to the-
Going back into, right,
form.
so it's
So
not
just
like,
return it back to it.
yeah, it's not like the PPO kind of disappeared into the void.
Right?
Mhm.
Okay, another question from students and then we'll have a couple of minutes. Okay. Go on, students. Go on, Ally. You have a question already?
Priyansh,
I'm in the middle of the yes.
Priyansh, yes.
Priyansh has a question.
You said that pressure has a high impact on temperature, and then you said, oh, pressure is not declining, it must be done in atmospheric pressure. So just clarify that.
Right, right. Do you want to take this question?
Sure. So I'm not, I don't know if there's like a slide. Pretty much like the recommendations is that like what the paper initially thought or like hypothesized with that they could combine pressure and temperature in order to kind of like maybe do the reaction, kind of like add a little bit of pressure and then maybe lower the temperature just to prevent any degradation of the blueberries. But what was actually found in the paper was that pressure actually caused a really high activity increase. So the recommendations of the authors was to just kind of discard, not do any pressure treatment and just do and continue on with thermal treatment. I hope that makes sense.
Yeah. Temperature, with the atmospheric pressure.
And also just to quickly elaborate on that, so like pressure has a higher effect in that it activates more polyphenol oxidase than temperature does, right? But we don't recommend that because we don't want to activate them. And
So
so,
what was the?
Yeah, so what's like the temperature that they say in the final that we add atmospheric pressure?
atmospheric pressure, they don't necessarily give a final recommendation, we just like read those numbers from the test.
Yeah, so their findings actually relate to the case study we saw in class. Because the case study in class, the combination of pressure
And
and temperature.
Right.
Reduced, reducing
Mhm.
the D value.
Yeah.
So yes, it's opposite.
So I assume that like if Sadiq perhaps ran the temperature and pressure assays as well, they'd probably find different results because they didn't have any latent PDOs. Versus they managed to keep that integrity of the enzyme.
Oh, could you go back one slide? So here you mentioned that the optimum pH is different because of the different blueberry varieties, but could it also just be because it's like the extracted enzyme? And because of that extraction process, and then also you see like a huge difference between the temperature. So if it was truly varieties, then that would be very difficult to apply this in a realistic application. Because you have almost like 40-degree difference between the two of them, so. Different comments.
All right.
If you guys.
I think like the variety was more so towards pH instead of temperature. But yeah, that is.
So but that's a good point.
Mhm.
Very different how it's variety compared effect.
Mhm.
The actual extraction.
Right.
Because it was both high bush blueberries too, right? And probably like slightly different subspecies, but. Yeah, it was really interesting.
Yeah, and then the final recommendation was nothing really new refrigerated.
Yeah. That's what they ended the paper and I was like,
After all of this,
yeah, like
they
they use like a giant tank and stuff to put the enzymes in. I'm like, that's all.
Yeah.
Mm, I don't know.
Okay, well, thank you guys. Good job, they were difficult.
Yeah.
They're all here then.
Definitely.
You did well in summary.
There you go.
Oh, no, oh, no.
I wonder why.
All right.
What? Oh. Where did you go? I'm gonna be like green. Yeah. I'm sorry.